Hello everyone, welcome to my talk, .NET Data Security, or .NET Core Data Security I should say, hope is not a strategy. My name is Stephen Haunts, and it's a big privilege to be here. It's a remarkable job that NDC and Dylan have done in making this conference go virtual at such short notice. So massive respect to everyone involved. Okay, so let's get started. So my name is Stephen Haunts, and I'm a Microsoft MVP for developer tools. I also run a training company called Stephen Haunts Training, although most of my in-person training is cancelled at the moment. And I also do training for a plural site, so I have 21, almost 22 courses on the site. So the reason I'm doing this talk is I believe it is a developer's responsibility when you're working at an organization to look after your company's data. And as software developers, we have quite a lot of power and responsibility in doing that. Quite often we see this kind of very blasé attitude towards companies, in that they think they're not going to get hacked or attacked or have any kind of data stolen. And really what they're doing is hope is not a strategy, basically. So hoping that you're not going to get attacked or have someone steal your data, credit card data, customer data, it's just not a strategy. It could be an external attacker hacking in from the outside like we see in the films, or it could be a member of staff who is disgruntled with the company, happens to have SQL developer or SQL admin access and select stars a load of data into a spreadsheet. These attacks can happen from pretty much any angle. So the hope that you're not going to have a problem is not a strategy. Now, quite a lot of time, and certainly what I've found in projects as well, is that really when you're working on a large scale project, security tends to get pushed back and back and back in the development cycle because it's not a big visual feature. Business people, they know security is important, but it's not something they can normally touch and feel. So generally it gets pushed back, which is a real shame. So what is this talk, or what's it not about, should I say? So it's not a talk about mathematics, which is good because I'm rubbish at maths. And it's not a talk about how to break cryptographic ciphers. And it's not about the CIA, the FBI, or the NSA, or anything like that. What this talk is about people like me and you who go into companies every day, sit down, we write code. And, just like everyone else, we're under tight deadlines. We have to get stuff out. And sometimes a lot of this security stuff really isn't that straightforward, and it's not generally that well documented. And you'll see from some of the class names we're going to look at today, some of it is a bit cryptic itself in .NET, which is kind of ironic. So a lot of what we're talking about is kind of, .NET, .NET Core, .NET Framework. Generally, a lot of this stuff gets used on the server side, although you can use, obviously, in client side as well. Now, when .NET Core first came around, sort of around the .NET Core 1.1 era, .NET Standard 1.6, the majority of the cryptographic protocols or algorithms that we wanted to use were not available with .NET Core, which meant .NET Core wasn't really, at the time, robust enough for the enterprise. But when we got to .NET Core 2 and .NET Standard 2, which I think was around summer 2017, that's when things really changed. So we started to get quite near feature parity with what was in the original .NET framework. And now, as we're going through future versions of .NET, we're actually getting more primitives being added in. So this talk is mostly about Microsoft technology. It's about .NET and .NET Core, but really the principles of what we're talking about kind of transcend any platform. So just because we're looking at a specific .NET API, what we're talking about is just as valid in PHP, Python, Swift, Ruby. The APIs will be different, but generally things are going to look very, very similar. Okay, so what we're going to cover, so we're going to cover quite a lot today. This is going to be quite a packed hour. So I appreciate everyone's probably very tired, and this is probably going to make you even more tired. So we're going to start off by looking at random numbers. Then we're going to look at hashing and HMACS, or hash message authentication codes. Then we're going to take a little detour and talk about passwords. Then we're going to talk about symmetric encryption using AES. We're going to talk about asymmetric encryption using RSA, and then we're going to talk about digital signatures. And once we've covered all of the primitives, we're going to start using some of them together to look at how we can combine some of these different primitives to build something bigger. So what we're going to end up looking at is we're going to build we're going to show a little sort of kind of theoretical demo of a system with Alice and Bob who want to send a secure message to each other. A bit like a very simple chat application. Now, as I said, we're going to cover quite a lot quite quickly. So if a lot of this stuff is very new to you, um, if you get to the end of the talk and you're thinking to yourself, oh my God, this is just too much, don't worry. Treat this talk as kind of an art of the possible. It kind of gives you a little glimpse into what you can do with encryption and cryptography. And I'm going to provide you lots of resources that you can go away with at the end of the talk if you want to. I'm going to give you lots of code resources you can download from GitHub, which are very easy to use. And I'm going to give you lots of book and sort of pluralsight course recommendations as well. So I think of this as kind of like your intro into the world. And then I'll give you lots of stuff that you can use afterwards. So saying that, this is where a real conference, people will be pulling their phones out and taking a photograph of the screen. But the GitHub repo I've got there contains all of the code from one of the versions of my workshop. So I'll do a one-day workshop. And all of what I'm talking about today is contained in that workshop. So if you do download that zip file or you clone the repository, in the complete folder, you can basically download the solution that's in there. It's all .NET Core compatible. And all of the examples in there are all self-contained console applications. So they're very easy to run, build, run, and step through. And it contains everything that we're talking about here. So if you do want to, spend a bit of time at your leisure going through some of this stuff, everything's in there. Okay, so what is cryptography? So generally we think of it as protecting information. We have some of the information, we want to hide it from people or make it unreadable. We do that using encryption. Encryption generally uses something called encryption keys. The result of what we encrypt is called ciphertext, and the art or the science of trying to break cryptographic algorithms is called cryptanalysis. But there's kind of more to it than that. So cryptography basically falls down into four distinct pillars. So we have confidentiality, we have integrity, we have authentication, and non-repudiation. So confidentiality is making something confidential so you can't read it. Integrity is about checking if something has become corrupted or has been maliciously tampered with. So we're going to look at some primitives for that. Authentication is about checking whether someone has permission to do something or check something, which is kind of an extension to the integrity model. And then we're going to look at non-repudiation, which is a good way of thinking about this is kind of like a contract. So if you sign a contract with someone for some work, say for, I don't know, £1,000 or €1,000, if you complete that work and then try and say, no, you're supposed to pay me €2,000, you have a contract in place so that one person can't refute it. This is going to be the computer equivalent of that. So cryptography is used pretty much everywhere. You cannot get out of bed in the morning without some kind of crypto going on. So online shopping, if you use Amazon or any other websites, generally that's going to be behind, TLS, and they're going to have lots of encryption going on with all your card details. When you use the cash machine, not that I guess many of us are actually using cash at the moment, but in the good old days when we used more cash, you put your card into the machine, you type your PIN number in, there's a cryptographic handshake going on between that machine and the bank to prove that you are the person who owns that card, and then you can withdraw your money. Smartphones these days, especially Apple, I'm not quite sure about Android because I don't use one, but as soon as you switch the phone on, pretty much everything is encrypted and locked down. But then there's kind of some other options as well. So things like Bitcoin and all the other 4,000 different types of coins are out there. They're all based around cryptography and how they work. And also electronic voting systems are starting to spring up as well, which use cryptography. Now, I'm not going to get into an argument about whether electronic voting is good or bad, but it is an area that it is being used. Okay, so let's start with our first primitive, which is random numbers. So random numbers are pivotal to everything we do in security. They are basically what we use to generate our encryption keys. Now, one of the easiest ways to generate a random number in .NET is to use system.random. If you're trying to roll a dice or generate lottery numbers, then system.random is perfectly fine. For generating non-deterministic encryption keys, system.random is not very good. A better one to use and a more deliberate one in the API to use is one called RNG Crypto Service Provider, which is in the System Security Cryptography namespace, as is everything else that we're discussing today. It's very easy to use, so I have a little bit of example code here. So we have a method called generate random number. We pass in a length, which is a number in bytes. So if you want a 32-byte number, you pass 32 into there. We instantiate the class. We create a new byte array of our desired length. Then we call getBytes, passing in that byte array. And then we get it filled with lots of random data, which is great. And then that gets returned as a byte array. Pretty much everything we're doing in the sample code you see today uses byte arrays. So sometimes you have to do a bit of conversion between byte arrays and maybe base64 encoded strings. But fundamentally, we're dealing with byte arrays at its core. That's random numbers. That's very simple. It's 7 or 8 lines of code. Next one is hashing. So a good way of thinking of hashing is it's a bit like creating a fingerprint for a piece of data. So if you have a document, say a PDF, and you run a hashing algorithm over it, you're going to get a big long number out the back of that hashing algorithm. So that number is called a hash. It is kind of like a fingerprint. If any of that data changes in that PDF document, so someone changes a name, or even if you just change one single bit in that document, recalculate the hash, the entire document will be completely different, or the entire hash will be completely different. This is a good way of checking integrity of files and data that we send across the internet. So there's 4 general principles or general guidelines for a hash algorithm. So first of all, it has to be easy to compute. I have some data, I pass in some data, hash it, we get a hash code out the back. It should be infeasible to generate a specific hash. So you can't start with a hash and go, what piece of data do I need to generate that hash? You can't do that. It should be infeasible to modify a message without changing the hash. So going back to my PDF example, and if you change just one single bit in any of that file, then the hash code will be completely different. And it should be infeasible to find 2 identical hashes. So if you have 2 pieces of data, two PDF files, if you generate a hash code for both of those files and the hash code is the same, then unless those documents are identical, you shouldn't be able to do that. That's called a hash collision. Some older algorithms like MD5 do exhibit that problem. Another good way of thinking about hashing and a good way of framing the mental model around it is when we talk about encryption, it's a 2-way operation. So we have some data, you encrypt it with a key, decrypt it with the same key, get your data back. So it's 2-way. Hashing, it's 1-way. So you can't find a hash for a piece of data and then reverse that hash into the original data. That's impossible to do. It's also what gives us one of the interesting, unique properties around hashing. There's lots of different algorithms out there. One that we're all probably familiar with is MD5, used quite a lot on Unix and Linux. So this produces a 16-byte hash value. It was designed by Ron Rivest in 1991. And, for a while it was quite well regarded. But in 1996, a collision resistance vulnerability was discovered where, you can have 2 different pieces of data that generate the same hash. It's still worth talking about today because if you're integrating with an older legacy system, you may still have to calculate MD5 hashes. So the sample code I pointed you to at the beginning of the talk, there are examples for MD5 in there. So I worked for a bank in the UK once called Egg, and we had a very old kind of AS400 mainframe system that sat in the back. And data that was passing between those systems regularly had to do MD5 hash checks between the data. So if you're working for an older legacy company or legacy system, you might still need to use it. So then we have what's called the SHA family, or the secure hash algorithm family. And there's various different variants that we have support for in .NET. So SHA-1 produces a 20-byte hash, or 160 bits. And in SHA-2, you can generate hashes that are 256 bits in length, which is 32 bytes, or 512 bits, which is 64 bytes. There is a newer one called SHA-3, and the main fundamental difference is that SHA-1 and SHA-2 had the involvement of the NSA when they were designed, which actually makes people a little nervous these days. So there was a competition to find a new hashing algorithm where the NSA isn't involved, and that was based on a cipher called KACAC, I think it is. Either silly name or bizarre name, but that is effectively what's become SHA-3. Now, this isn't natively supported in .NET Core yet. I imagine it might come at some point in the future, but at the moment it's not. You can find C#-based open source implementations of it, but obviously you need to use anything like that at your peril, and that's a discussion you have with your security officer. What we're going to look at today, we're going to use SHA-256. So again, it's very easy to use. Most of what we're looking at today is actually quite easy to use. So we have a method here, compute hash SHA-256. We pass in a byte array of the information we want to hash. So this could be, our PDF file that we've loaded up into a byte array. We call the static create method on the SHA-256 class, and then we call compute hash, pass in the data that we want to hash, and that will give us a byte array back that we return. So in this case, it will be 32 bytes in length. So that was hashing. So there's a kind of a next logical step for hashing called authenticated hashing. Now this is very, very similar. So as you can see, we have the green box is the hashing algorithm. We pass some data in, we get a hash out. But in this instance, we also pass a key into the hashing algorithm. So for example, the one we're going to look at, the key is 32 bytes in length. So what this means is that if I hash a piece of data, I have a key. I then send that piece of data or that hash code and a piece of data to someone else. If you want to calculate that same hash, you have to have the same key. If you pass a different key into it, you're going to get a completely different hash code out the back. So this is why we call it hashing. So if you think of it, your mental model is that the key is kind of like a password. You both need to know the password to create the same hash. This is where the authentication aspect comes in. So all your recipients have to have that key. Now, sharing these keys is very, very difficult. We're going to talk about that later. But fundamentally, for now, everyone that wants to recalculate that same hash has to have the same key. So this is used for verifying both integrity and authentication. Integrity in that we're calculating a hash for a piece of data. We can easily tell if that piece of data has been tampered with because the hash will change. Hash codes or HMACS are based around MD5 and the SHA family, just as we looked at before. And strength is based on the length of the key. So the longer the key you provide it, the more secure this thing's going to be. So the most common attack against HMAC is a brute force attack, which is where you try billions of combinations of keys until you get the one that you want. Obviously, the longer the key, the better. Okay, very simple to use. Looks kind of similar to what we looked at before. So we have a method, we pass in our data that we want to hash. We also pass in our key. So our key is going to be a 32-byte random number in this case, generated in the same way that we looked at earlier with RNG crypto service provider. So if we want to do a SHA-256 based HMAC, we instantiate the HMAC SHA-256 class. We pass the key into its constructor. And once we've done that, we call compute hash on that object, pass in the data that we want to hash, and then out pops our hash on the other side. So very, very powerful concept, what it lets us do, but just a few lines of code to use it, which is fantastic. So while we're talking about hashing, I want to take a little sort of detour down the road of passwords. It's something that affects us all. So storing passwords securely is very, very important. You only have to look every day when you see Troy Hunt posting on Twitter there's been some massive data breach and a whole load of passwords have been stolen, or maybe you've signed up for Have I Been Pwned and you've received one of his password breach emails. I've had that several times. So storing passwords is very important because they do get stolen and people do manage to reverse engineer them very, very easily, which we'll look at in a moment. So the way that we store passwords in our system, if you're doing it by hand, is very, very important. So there's two common attacks that we can use against passwords. One is a brute force attack. This is where you try billions and billions and billions of combinations of passwords until you get the password to hash till you get a password that produces the same hash as what you'd store in your database. Typically, passwords are stored as hashes. So brute force attacks, whilst it sounds like a big job, is actually becoming easier every year. I mean, every time NVIDIA releases a new GTX card, I mean, that's, we use graphics hardware as the means for brute forcing passwords. Most common tool for doing it is a tool called Hashcat. Very easy to use. You can just download it. You can download a dictionary from somewhere, or you can get it to brute force a password and it will just transfer away cracking passwords for you. The other attack is called a dictionary or a rainbow table attack. And fundamentally what this is it's a file which could be multiple gigabytes in size, which has pretty much every single password you can think of and all of the variants, where we try to be clever by changing vowels into numbers and sticking exclamation marks all over the place. attackers have thought of all this. They're not stupid. So all of these combinations are in a dictionary, and then that's all a hashcat has to do is it just looks in the dictionary. It's literally just a dictionary lookup. A good way of demonstrating this, if you're trying to scare people in your organizations to take password security more seriously, so there's a website here called crackstation.net. This is quite a nice little tool. So you take a password, so in the grey box here we have a SHA-256 password, you paste it in there, you fill out the captcha, hit crack hash. As you can see here in the green at the bottom, it's worked out that it's a SHA-256 hash and the password was secret69. And on this same website, you can actually pay them a few dollars or whatever it is, and you can actually download the dictionary that they use on the site. So what we talked about here then is, the most common way of storing passwords is to take a password that a user types in, you hash it with say SHA-256, and you store the hash in your database. That's been a very common way of doing it for years. Now, normally when I can see the audience, I ask people to put their hands up and tell me whether their companies do this. I can't really see that many video feeds on, so we won't bother with that bit. So the next common way of doing this is what's called a salted hash. Now, this is fundamentally very similar, except what we do is we append onto the password something called a salt. Now, the salt is just a piece of entropy that you add on to the password. So it could be a few digit number, or it could be a 32-byte random number that you append onto the password. You hash that password, and then you store that hash in your database, but you also have to store salt as well. Maybe not necessarily in the same table as the password, but you do need to store it somewhere, so that when the user retypes in their password on a system, you look up that user, you bring their, you pull back their salt, combine it with the password, do the hash, and then check with what's in the database. This is incredibly common. I'd say probably 50, 60% of companies out there still do this. And that's fine. The problem with this though is, whilst that might be a secure password now, and it might take hashcat decades to try and crack those passwords, as GPU hardware gets more powerful, and it does, the rates in which GTX or NVIDIA and AMD cards is progressing is quite scary. What might be a secure password now with Assault, in 5 years' time, could be not secure. So that's a big problem. So there's another technique that we want to use, which is called a password-based key derivation function, which sounds lovely, or a PBKDF2, if you want to really impress people with acronyms. But what it's doing is actually quite simple. So it's the same as before. We have a password and we have a salt, but we also have a number, which is called a number of iterations. So if you pass 10 into number of iterations, it's going to rehash that password with the salt 10 times before it gives you the final password. If you put 10,000 in there, it's going to hash that password 10,000 times. Put 1,000,000 in there, it's going to do it 1,000,000 times. Now, the reason this is important is because what it's doing is it's algorithmically slowing down the password hashing process. So instead of hashcat being able to crack, say, I don't know, 1 billion passwords a second, you might slow it down to 1,000, 100, 10, or 1, depending on what that value is that you put in there. So I'm sure you've all seen on some websites when you log on, go to the website, you type in your username and password, and it feels like there's kind of like a 5-6 second delay before anything actually happens. Behind the scenes, they're probably doing something like this. You're probably waiting for their PBKDF2 function to run. But this is a great way of doing it because it's slowing down that password hashing process. So if you want to do this in .NET, it's very, very easy to do. Now, there's a class that we use called RFC2898 derived bytes, which is a lovely piece of class naming. If you're intimately familiar with RFC spec numbers, then that completely makes sense. For the rest of us, normal people who aren't familiar with RFC spec numbers, it's a bit confusing. So if you're flicking through the documentation for .NET, you're probably going to skip over it because it just doesn't make sense generally. But it is incredibly easy to use, which is great. So in our method, we have the password to be hashed, we have our salt as a byte array, and we have an iteration number that we pass in. So we instantiate RFC2898 derived bytes, pass those 3 values in, and we call getBytes20, and that gives us our hash code back. And the reason we pass 20 into getBytes is because behind the scenes, the RFC2898 spec uses SHA-1 to do its hashing, which gives you a 160-bit hash code back, which is 20 bytes. So that spec specifies that you use SHA-1, so that's what Microsoft has implemented. So you only need to bring back the first 20 bytes. Once you've run that, you then go and store your password in the database, along with the salt as previous. Your system obviously needs to know what the iteration counter is, so that's probably going to be stored in some secret config somewhere. Now, quite a while ago when I wrote the original version of this talk, I did some timings on a much slower laptop than what I'm using today, but it kind of illustrates a point. So 100 iterations at the time took 2 milliseconds, 1,000 took 16 milliseconds, right the way up to 500,000, which took 7 seconds. Now, 7 seconds, you might be thinking, no way am I going to make my users wait 7 seconds. So what you need to do is you need to have a conversation between your security officers, organizations, and people in the business. And you have to work out what your tolerance to that delay is going to be. The company might turn around and say, okay, well, 3 seconds is okay. Or if you're Amazon, they might say, well, no, that's 3 seconds is like $1 billion to us. So you need to, check that number, or check what number you want to use. Over time, you may want to change that number. So as servers and computers get faster, if you had 500,000 as your iteration count today, 5 years' time, obviously that could be a lot shorter in length. So organizations I've worked in, so we might have had, say, 100,000 as our iteration count, and then we wanted to double it, say, every year to 200, by 100,000. One easy way of doing that is that if you want to do a gradual rollout of those changes, then you just have a bit of logic in there that says, when your user logs in, you automatically invalidate their password, and then you spin them some yarn about how we want to improve our security, get them to type in their password again, rehash it, and then store it. Or you could have a more brute force attack system where you invalidate everyone's passwords and then try and get them to relog back in. That's probably the easiest way of doing it. Now, I'm sure everyone's familiar with Ashley Madison. It's been discussed at conferences for quite a few years. If anyone's not familiar with Ashley Madison, it's a dating website that encourages people to have affairs, not a particularly pleasant website. But a few years ago, they had a big data breach, very big coordinated attack against them. So all of their data was stolen, including all of their passwords. But behind the scenes, when they tried to crack these passwords, they found that they used a system called bcrypt for hashing their passwords. Now, bcrypt is very similar to what we've just looked at with the password-based key derivation function. Interface-wise, it's the same. Data to hash, a salt, an iteration number. The main difference is bcrypt uses, is it Blowfish? I think it uses. It uses a different algorithm internally. That doesn't really matter. They'd used an iterated hash function, which is good. But another problem with Ashley Madison is they also stole the source code, which is a big problem as well. So they went through the source code and they found that some enterprising developer, maybe a junior developer, I don't really know, had come along and tried to optimize the logon process. So when you logged in, it would then cache an MD5 token of your password, so that the next time you log in, if you had that token, you could just check that instead, and it would log you in faster. Which, for someone who doesn't know how these things work, seems like a fairly reasonable optimization. Once they'd found this out and knew where the tokens were, they managed to go reverse about 90% of all of the passwords in their database, which was a bit of a problem for them. There's a link here to an Ars Technica article that kind of goes through this whole Ashley Madison thing in a lot more detail. Really interesting. I highly recommend reading it. Okay, so the next one we want to look at then is symmetric encryption. I hope everyone's still following me so far. Can't really see anyone on the screen. You've all got your cameras off, so never mind. Okay, so symmetric encryption. The way this works is we have some data. We encrypt with a key, which gives you your ciphertext or your encrypted data. Then use the same encryption key to decrypt the data, and you get your original data back. That's why it's called symmetric. It's the same key for both encrypt and decrypt. Now, encryption this way is good in one way. It's very, very fast. It's algorithmic. It's what computers are good at. But the problem is sharing those keys between people is very hard. I mean, how do I get my encryption key to someone? Don't want to email it. Probably not going to send it on WhatsApp or stick it in a database somewhere. So that is a particular problem of symmetric encryption. But the actual speed of symmetric encryption is very, very fast. So as you said before, going back to our mental model, whereas we said hashing was one way, encryption is two-way, because you want to be able to recover the data that you've encrypted. And the way symmetric encryption works is it encrypts several bytes at a time. So these bytes are called blocks. So blocks are padded, so each block is the same size. So if you've got a piece of data and you say you've got a block size of 128 bytes, once you get to the end, if it doesn't quite fill up 128 bytes, it'll get padded with some known data or zeros. So in .NET, all of our encryption algorithms derive from a class called Symmetric algorithm. So the one that we care about today is AES Crypto Service Provider. But we do have implementations for DES Crypto Service Provider and Triple DES Crypto Service Provider. So those are much older encryption algorithms, not recommended for use in new systems. As I said before, if you're integrating with something that's a lot older and legacy and you have to decrypt DES encrypted data, it's handy to know how to do it. But because each of these algorithms inherits from that same base class, the interfaces are the same. So once you know how to use one, you know how to use all of them. So AES, it's a standard with the National Institutes of Standards and Technology. It became a standard in 2001, so it's quite old now. And it was designed by two Belgian mathematicians, so Joan Damon and Vincent Ryman. And it's based on a cipher called Rindale. So some of you may have seen that there's a Rindale managed class in .NET, as well as AES Crypto Service Provider. Fundamentally, they're both the same, pretty much the same. But it was based on the Rindale cipher. So the way this works is if we want to encrypt some data, we pass in our plain text, so a byte array of the data we want to encrypt. We pass in something called an initialization vector, which in this case is going to be a 16-byte random number. And that's used to help actually kickstart the encryption of the first block. Now that number, that IV, it's not a key, it's not secret. You don't treat it the same as you treat a key, but you do need to store it. Because when you go to decrypt your data, you need to pass the same IV into AES. And we have three key sizes we can use: 128 bits, 192 bits, or 256 bits. We're just going to go straight for 256 bits, because the bigger, the better. So you pass those three things in, you run the algorithm, then you get your ciphertext out the other side. So in .NET, you've got two versions of this class. You've got AES Managed and AES Crypto Service Provider. Both do exactly the same thing and are most likely going to give you exactly the same results. The main difference is that AES Managed is a native .NET implementation, so it's written in probably C#. It's an IL-based implementation, but it's not a certified implementation. So there's a ratification process called FIPS, and it's FIPS 197-2. So this version isn't 197-2 certified, whereas AES Crypto Service Provider is. Now this uses the underlying Windows crypto platform, or if using .NET Core on a Mac, it uses Secure SSL. This one is FIPS certified. Now what that means is it's been officially tested. So that means if I encrypt some data on my machine here in .NET Core and pass it over to another system that's implemented in Java, and their version is FIPS certified, we can guarantee that they're going to be able to decrypt my data that I sent them, and vice versa. So that's what that certification means. So slightly more complex to use this, but this is probably the most complex piece of code we're going to look at today. So we have our encrypt method. We pass in our data to encrypt. We pass in our key as a byte array, and we pass in our initialization vector, which is 16 bytes. We instantiate AES Crypto Service Provider. Here I'm explicitly setting the keys. And we create a memory stream and a crypto stream because it's stream-based, which means you can encrypt very large amounts of data. We pass the data in. We call cryptostream.write, then flush, then we do toArray, then that gives us back our encrypted data. Now, decryption is very, very similar. So most of that code is the same. So it's a bit difficult to point to the screen, but the line here where it says new crypto stream, open bracket memory, comma, it says AES creates decryptor there, whereas on the previous slide it said create encryptor. That's the only difference. So you create the stream, write it, flush it, call to array. That gives you your original data back as a byte array. So if it was text, so if it was like someone's name from a database, you'd probably pull that back as, you'd have it as text. You convert it to a byte array, you encrypt it, then you're probably going to base 64 encode that result to store it in your database. When you want to decrypt it, you're going to, unbase 64 encode it back into a byte array, decrypt it, and then convert it back into a normal string. Now in .NET, up till the current versions of .NET, .NET Core 3, there's different modes of AES that we can use. And we use one called AES cipher blockchaining mode, which is kind of its default mode, and that's typically what we'd use. Now, in normal usage, what we'd do is we'd encrypt some data using AES, and then using the same key, we'd create a hash map of the encrypted data. So then we know that once we've sent that data to our recipient, if they've got that key, they can check the hash map first to make sure the data hasn't been tampered with. If it hasn't, they can then decrypt it. So that's called an encrypt and then MAC. Now in the latest version of .NET Core, we have a new mode for AES called GCM mode, which is called Gallius counter mode. So what this basically does is it takes that hashing process at the end, but it does it internally whilst it's encrypting, which makes it quite fast and efficient, and you're getting your hash map by default. So this looks slightly different to use, but it is quite straightforward. So here we have some text that we want to encrypt. So Mary had a little lamb. Now we pass in 3 pieces of data. Now we have a nonce, which is basically fundamentally the same as the initialization vector, but in the spec it's called a nonce, number once. In this case it's 12 bytes. We pass in our key, just the same as we did before. And then we can also pass in something called associated data. Now this is just metadata that you can pass in along with your data that you want to encrypt. Typically when I've used it, I've just passed it null, so I've never sent associated data in. But imagine if you had a customer record, name, address, telephone number, that sort of thing. The associated data might be the key ID for the database, for example. So you pass all of that in, and I just realised I've got a mistake on this slide, and I'll explain. So you run all of that, you get your ciphertext out the bottom, but you also receive another piece of data out of it called a tag, which is a byte array of data. Now that tag is your hash map. So you're receiving 2 things back out of this. So I need to go and fix that slide. To use GCM mode, it's nice and easy, which is great. So we have our encrypt method. We pass in our data to encrypt, pass in the key. We pass in the nonce, which is 12 bytes. It's a random number. You generate a new nonce every time you encrypt some data. And we have our associated data. So then what I do is I pre-initialize some arrays. So we have the tag, which is 16 bytes. So the hash map we get back is 16 bytes. We then initialize an array for our ciphertext. We create the AES GCM class by passing in the key. We call encrypt, where we pass in our nonce, our data to encrypt, the ciphertext array we want to fill, the tag that we want to fill, and the associated data. And that gives us back our ciphertext and our tag populated. So in this case, I'm just returning a tuple or a tuple, depending on where you're from in the world. That gets returned back to the client. So to decrypt, what we do is we pass in what looks like 100 things into our method. So we pass in our ciphertext, that's our encrypted data. We pass in the original key. We pass in the original nonce that was used to encrypt the data. We pass in the tag that we was given from the encrypt method. We pass in the associated data, pass all that into our decrypt method, and then we get our data decrypted. So if any of that ciphertext has changed, or the tag has been modified, or the nonce has been modified, or you pass in the wrong key, you're obviously not going to be able to decrypt the data. So all of those things have to be the same. Okay, asymmetric encryption. So this is fundamentally we're trying to achieve the same thing. We're trying to take some data, we're trying to scramble it, in a way so that people can't read it, and then we want a way to decrypt it. The way this works with things like RSA is instead of having one key, we have a key pair, a public and a private key. So what we do is we encrypt with our public key, and then our recipient decrypts with their private key. So if I'm sending my data to, let's pick someone in the audience, is Jessica on there? We'll pretend Jessica's here. She said she was going to turn up. So if I wanted to send some data to her, I would request her public key. She would send that to me. It's public, anyone can know it. I'd encrypt the data with her public key, send her the encrypted data, and then she would use her private key, which only she knows, to decrypt that data. That's how things like RSA work. So this was developed by RSA Data Security Incorporated by Rivest, Shamu, and Edelman, hence the name RSA. And the way this works, it's based around very, very large prime numbers and modular arithmetic. And it's based around the way that there's no efficient way to factor very large prime numbers. So a minimum recommended key length is about 2048 bits for the key, so they're quite big. But typically you might use 4096-bit keys. Now RSA is a mathematical encryption scheme, and there is a limitation. You can only encrypt data up to the size of the key. So if you've got a 4096-bit key, you can't encrypt a piece of data larger than that, which is a little bit of a limitation. You could say, well, I could just get my data and split it into lots of chunks and encrypt those. But you're probably not going to want to do that because RSA is insanely slow compared to something like AES. So as I said, it's based around prime numbers and prime number factorizations. So if I said to you, what's 23 times 17, and that's easy. Work it out in your head or on a calculator, it's 391. Now, if I was to turn around and say, what two prime numbers do I multiply together to make 5,963? Normally I make the audience sweat at this point trying to work it out, but I'm not going to do that now. It's much harder to do. So the answer is 67 times 89 is 5,963. So if we bring that back into our key analogy, so the public key is the 5,963, it's the easy bit. And the bit that was hard, trying to work out those two prime factors, is the private key. So going back to our example, if I'm sending some data to Jessica, she would have both of those keys. I would request her public key, 5963, encrypt the data, send it to her, and then she uses her private key, the 67 times 89, to decrypt the data. So it all sounds a bit complex, but it's actually very easy to use. So if I want to generate a key pair, public and private key, I create a class called RSA Crypto Service Provider, passing my key length that I want. And I then call RSA.export parameters false to give me the public key, and then RSA export parameters true to give me the private key. That's kind of interesting API design there, passing in true and false to get the public and private key, but that's kind of how it works in .NET. So to encrypt some data, now that we've obviously generated those two keys, so I pass in my data that I want to encrypt. I then instantiate RSA Crypto Service Provider. I import my public key, the recipient's public key, and I then just call RSA.encrypt, passing in the data, and it gives me back the encrypted data. So if we now assume that I've sent that data to my recipient, they come along, they instantiate Crypto Service Provider, RSA Crypto Service Provider. They import their private key, because it's their key, only they know it. They call decrypt by passing in the encrypted data, and they get the encrypted byte array back out the other end. Sorry, yeah, they get the decrypted byte array back. So that's, it's quite easy to use. It's very, very powerful. Gives us this ability to have this split key system, which we're going to come on to why that's useful in a moment. Just quickly, I want to finish off the primitives by looking at digital signatures. So a digital signature is something that's based on RSA. It uses the public-private key scheme. A good way of thinking of a digital signature is you can have a piece of data and you can have it digitally signed with someone's private key, so that if anyone further along tries to refute that data that they've been sent, because it's been encrypted or signed with a private key, you can kind of prove who signs that message. A great way of thinking about this is if you've used any websites like DocuSign, where you can go on and sign contracts. what that's doing behind the scenes is creating digital signatures, so that if anyone signed a contract on there, buying a house or car, you signed that you're going to pay one value, but then you try and refute it by saying you want to pay a different value. That document has been mathematically signed, which you can use as evidence in court, which is quite handy. So 3 parts to a digital signature. We have key generation, we have the signing algorithm, and a signature verifier. So the way this works then, so what we want to do to create a digital signature, now we talked about the limits with RSA in that you can only encrypt up to the size of the key length. Well, that's the same with a digital signature. So what we do first is we get our data that we want to sign. Now this could be a PDF of contracts that people have physically signed or whatever. We then take a hash or a HMAC of that document. We then sign the hash, and that gives us our digital signature. So if we look at my brilliant piece of art here, so we have Bob. So Bob gets his private key and he creates a digital signature. He sends that digital signature over the internet, and then Alice here uses Bob's public key to verify that her signature is true or not. Now, when we talked about RSA, we talked about the fact that you encrypt with a recipient's public key, then they decrypt with their private key. So here it's the other way around. So the sender is using their private key to basically create a signature, and then the recipient is requesting his public key to verify that signature. Excuse me. So generating keys for digital signatures is exactly the same as what we saw before. So I won't cover that again. So then to sign the data, so we pass in the hash of the data that we want to sign. We instantiate RSA crypto service provider. We import the private key. And then we have to create a class called RSA PKCS1 signature formatter. It's a brilliant piece of class naming. We then have to tell it what hashing algorithm we're using internally. So obviously we're passing in a hash. So to set that, we had to pass in a magic string that says SHA-256 in all uppercase. I kid you not. And then what we do is we call create signature, we pass in that hash, and then what that's going to do is it's going to return a byte array of our digital signature. So we've digitally signed our PDF, we've sent it to someone, and they want to verify that their signature is valid. So what do? So they take the hash of the data. So we send them the hash, we send them the signature we just calculated. They import the originator's public key. We then call RSA PKCS, well, we then instantiate RSA PKCS1 signature deformatter. So it's formatter before, now it's deformatter. Again, we tell it what hashing algorithm we're using, so SHA-256. And then we call verify signature, and that will return true or false. True if it's a valid signature, false if it's not. Okay, so I'm going to need to get a wiggle on here because we're running out of time. So we have quick recap. So confidentiality, we looked at AES and RSA. Integrity, we looked at SHA-256. Authentication, we looked at HMACS. And non-repudiation, we looked at digital signatures. So each of those 4 pillars, we now have a very simple primitive that we can use to satisfy those pillars. So what we'll do now is we'll combine some of these together. Now, as I said before, this bit's going to go reasonably quickly. But if you are interested in how this works, download the source code I said at the beginning. I'll give you the link at the end. I'll post it into Slack because I've got very simple console apps with all of this stuff in that you can run and step through really easily. So, hybrid encryption. So RSA has limits on the amount of data you can encrypt. We've already discussed that. But we want the flexibility and speed of AES. But sharing keys is hard. So what we're going to do in this first instance is we're going to combine RSA and AES. And what we're going to do is we're going to have Alice and Bob, and they're going to send a message between each other in a secure fashion. So what do we do then? So we start off, we take we generate an AES session key. It's just a 32-byte key that we're going to use for this particular conversation. We encrypt our message using that session key, using AES, just like what we looked at before. And then what Alice is going to do, she requests Bob's public key. He sends it to her, and she encrypts her session key with RSA using Bob's public key. She sends her encrypted message and her encrypted key over to Bob, and an initialization vector as well, I should add. Bob then uses his private key to decrypt the AES key. Once he's done that, he can then use that AES key to recover the original data by decrypting it with AES. So fundamentally, that's quite simple. So if we was imagining that as a packet of data or a class of data, we have our RSA encrypted session key that we're sending. We have our initialization vector. I just realized I left off the previous diagram. And we have our AES encrypted data. So let's run through this as a quick example. Let's walk through the problem. So AES, so Alice generates an AES key, 32 bytes. She generates an initialization vector, 16 bytes. She encrypts her message using AES, session key, and the initialization vector. She encrypts the session key using Bob's public key, packages it all up, sends it over to Bob, and he receives the message. So he takes that message, he uses his private key to decrypt the session key. So he's now got the original session key back. He then uses that session key and initialization vector to decrypt the message. So the message is, meet me at noon below the clock tower, wear a red rose in your button. So what we've done here then is we've managed to get a symmetric key between two people securely using RSA. That's the benefit we've got here. So Bob now wants to send a reply, so he generates a new key. So every session, you create a new key. He creates a new initialization vector. He encrypts his data using the key in the IV. He he encrypts the session key with RSA using Alice's public key, so he's had to request Alice's public key this time. Encrypts that, sends it across. Alice receives a message. So now she wants to decrypt the message. So she uses her private key to recover the session key. She then uses that session key and initialization vectors to decrypt the message. And it says, I will meet you. I will be wearing a blue hat and red boots, because Bob is very fashionable. We like Bob. Great. So we've got data backwards and forwards between two people relatively easily using RSA and AES. Brilliant. What can we do now? So we want to add integrity into this now. So exactly the same as what we did before, except we had this orange blob in the middle. So once we've encrypted our data, once we've encrypted the key using the recipient's public key, we then create a HMAC of the ciphertext in the initialization vector. Now we create a HMAC because we have access to that session key, so we may as well use it to create the HMAC. We then store that HMAC in a packet of data, and then on the other end, Bob has to he has to decrypt the session key first with RSA, his private key. Once he's got the session key, he can then recalculate the HMAC to make sure it hasn't been tampered with. If he's happy, he can then go and decrypt the data. So again, if we think of that as a packet of data that we're sending, so we have the encrypted session key, the initialization vector, the encrypted data, and a HMAC of the encrypted data and the IV. Now this example here is using AES in cipher blockchaining mode. So if you have to use an older version of AES, it uses cipher blockchaining, or you've got some legacy code, or an older version of .NET, then this is how you do it. If you're using .NET Core 3, you would use AES GCM mode. Now, the beauty of GCM mode is it does that hashing process for you internally. So our original diagram here, that we have here looks very much like the original diagram that we looked at the beginning of the hybrid encryption section. So if you're using GCM, you don't need to do that additional hash process, which is good. But you would have a slightly different packet that you send. So you'd have your encrypted session key, you'd have the nonce that you generated, you'd have encrypted data, and you'd have the tag, which is effectively that HMAC. Great, so let's go one step further. So we've conquered confidentiality because we've managed to encrypt data and we've managed to swap the keys. We've used integrity and authentication because we've used HMAC, either internally in GCM mode or manually. So we have integrity and authentication. You have to be in possession of that decrypted AES key to calculate the same HMAC. That's authentication. If any of the data has been tampered with, then the HMAC isn't going to match the one that was sent to you. You recalculate it, so that gives you integrity as well. So let's add a digital signature into the mix. So what we do here is once we've calculated that HMAC, we can then pass that into our digital signature algorithm, create a digital signature using the recipient's private key. So that then means that when that gets sent across to the recipient, they then have to use the sender's public key to calculate the digital signature. But they can't do that until they've decrypted the session key. So they decrypt the session key, they check that the hash is valid by recalculating it. If it is, they check whether the signature is valid. If it returns true, they then go and decrypt the original message. Now that sounds like quite a lot. We went through that quite quickly. But as I said, if you do want to play around with it, it's not actually that complicated once you start stepping through some code. So I do encourage you to download sample code. Just have a play around with it. I've documented it all fairly well, I think. And once you actually start playing around with it, it actually becomes quite a bit clearer. And what we discussed here is kind of a very rudimentary way in which a very simple, two-way chat system might work in the way that you're sending data between people. Also, if you think about when you're using a server, you go on the internet and then it's a secure website using HTTPS, so you've got a TLS connection going on. What we've just described is very similar to what TLS is. So your server or your website and the server will negotiate initially. They'll agree what ciphers they're using. So they might go, let's use RSA, let's use AES, let's use HMAC 256. So once they've agreed on the protocols they're going to use, your machine will then create this session key. It'll encrypt it, send it across to the receiver. So that means they've got the session started. And then any traffic you send over HTTPS is going to be using that symmetric key that's already been shared. So, similar principle. Okay, we've covered quite a lot here. So that's what we've gone through today. I'm not going to read through it all again. We've gone through it at length. But the stuff that's in .NET is, and many other systems, it's very powerful when you get to start using this stuff, and it's actually fascinating. So if you are still interested after this, here's some things that you can use. So there's 3 really interesting books here. So the first one on the left, Code Book by Simon Singh, is written for mere mortals to understand. And it's kind of like a history book. So it starts from ancient times and it goes right the way through to reasonably modern times. It's a fascinating read. My wife was horrified once when I read it on holiday. It kind of reads a bit like a novel. Book in the middle, Everyday Cryptography, is quite an advanced book. So the first half talks about all the primitives we discussed today, but it tells you how they work internally. It's quite an in-depth book. And the second half of the book talks about how they're used every day. So one section in the book talks about how a cash machine on ATM negotiates with the bank, and it goes into a lot of detail how that works. Fascinating book, but it's quite heavy going. Applied Cryptography on the right there is the book that in the 90s the NSA tried to ban, basically, because back in the day, encryption algorithms weren't allowed to be exported from the US. They were classed as munitions, and this book obviously upset a lot of people. But it goes into a lot of detail about how a lot of these algorithms work. It doesn't cover AES, unfortunately, because it wasn't around at the time. But if you like maths and you're a glutton for punishment, that's a really good book to look at. If you're a Pluralsight subscriber, I've got a few things that you might find interesting. So my course, Practical Cryptography in .NET, basically goes through what we've done today, but at a much slower pace with a lot more explanation. So it's about a 4-hour course. I'm planning to update this course soon to make it fully sort of .NET Core. So the examples you download and the demos I do in that course are .NET Framework, but apart from the project file differences, most of the code is completely identical. So the course is completely valid, but I am planning to update it at some point soon. One at the back, play-by-play enterprise data encryption with Azure Revealed, is a course I did with Lars Klintz where we talk about Azure Key Vault, if anyone's interested in that. And this last course here, Blockchain Principles and Practices, is a course I wrote about blockchain. The main principle of the course is that if your CTO turns around to you and says, I want a blockchain, which they seem to do quite a lot, this course tells you exactly how they work, what it's all about, and it builds up an example blockchain in C# using some of the techniques that we discussed in this talk. So if you think of this course as a bit of ammunition that you can have when your CTO says he wants a blockchain, he'll give you the ammo you need to turn around and say either, yes, that's a good idea, or no, that's a terrible idea. No is normally the correct answer. So thank you very much. I've managed to finish 1 minute before the end. That's quite amazing. I have a blog at stephenhaunts.com where I blog about all sorts of things. I'm on Twitter at stephenhaunts. Be great to interact on there. Maybe once this whole pandemic nightmare is over, maybe I can come back to Porto another year and I can run my 2-day, essentially run my 2-day security workshop, which you might find interesting. But apart from that, thank you very much for having me. I know obviously doing a virtual conference has been very hard for everyone. It's a lot of screen time for people, and a lot of us speakers have had to grapple with how to do this, but I think it's gone fairly well. So again, thank you very much to NDC and Dylan Beattie for pulling this all together. And thank you very much to everyone for attending. So thank you.